This Zoom session is being brought to you by the Fractal Crystal Ball. We'll be doing 1.3 and 1.4. 1.3 is on function graphs. Okay. I like to say that this is more mathematical grammar than mathematical vocabulary. Vocabulary equivalent will be when we get to sines and cosines and their definitions and so on. This is sort of a more general concept, the function. A function is a rule that takes an input called x, and computes an output called f of x, written f, parent, x, and parent. So it's sort of like a machine. You put x into it, and f of x comes out of it. So in a sense, this calculator is a box full of functions. The domain of f is the set of all possible inputs. The range is the set of all possible outputs. Now, okay, you find the value by substitution and evaluation. So for example, if f of x equals 3x squared plus 2x minus 4, let's evaluate f at 0, 1 at negative 1. At 0, you plug in 0 in for x, 3 times 0 squared plus twice 0 minus 4. After a bit of calculating, it comes out to negative 4. F at 1, you plug in 1. And just a second, Ryan Lee just entered the room. Okay, 3 times 1 squared plus twice 1 minus 4. After a bit of calculation, it's 1. F of negative 1, you plug in a negative 1 here and here. 3 times negative 1 squared plus twice negative 1 minus 4. After some calculation, that's negative 3. The graph of a function, the set of points in the Cartesian plane with coordinates x by f of x. So here's this point over x up f of x. Since a function is defined to have one value, f of x, for each value of x, that means for any vertical line corresponding to an x, there has to be one point it meets the graph, or at most one point. That's called the vertical line test. So this is the graph of a function because every vertical line meets it once. This is not because vertical line meets it at 1, 2, 3 points. In a sense, you could say that this defines not one, but 3 separate functions. The one with the graph from here to here, the one with the graph from here to here, and the one with the graph from here to here. All right. Now, we define domains in terms of, a function's domain is where f of x is defined. And in general, this will consist of no division by 0 and no square roots of negatives. Later, we'll get to what are called complex numbers, but not yet. So in a certain sense, the domain is relative to the kinds of numbers you're willing to admit. So for example, here's f of x is 1 over x squared minus 9. So the domain is where x squared minus 9 is not 0, and those will be every numbers except positive 3 and negative 3. So x not equal to plus or minus 3. G of x equals root of x minus 5. Well, this x minus 5 has to be at least 0, so x has to be at least 5. So it's this half of the plane, including the endpoint 5. Now here's something you'll be seeing a lot later, a lot more of, when you get to the calculus. It's something called the difference quotient. The idea is that given 2 points on the graph of a line, what is the slope of a function? What is the slope of the line between them? So here's a point x by f of x. You move over a distance h. So here's a point x plus h by f of x plus h. So here's a line through those 2 points. Its slope is called the difference quotient. It's a change in f divided by the change in x. F of x plus h minus f of x in the numerator divided by x plus h minus x in the denominator. A little bit of simplifying, this denominator just becomes h. So f of x plus h minus f of x over h. In calculus, this is denoted delta f over delta x, where delta is the Greek letter d, meaning difference, capital D. So it's the change in f divided by the change in h. So it's a rate of change over the interval from x to x plus h. So examples. Is the square root of x, cube root of x a function? Yes, for any x, a cube root is defined. Is 2x squared plus 3x plus 1 a function? No, it is not, because 0 by 1 over root 3 and 0 by negative 1 over root 3 are both on the graph. So there's a value of x for which 2 values of y apply. So not a function graph. Here we have the function 3x squared plus 2x plus 4. We want to know f of negative x, negative f of x plus 1, f of 2x, and f of x plus h. Well, f of negative x, you plug in a negative x here and here at 3 of negative x squared, twice negative x plus 4. The square of negative x squares away the negative. Here, the negative stays. So you get 3x squared minus 2x plus 4. Negative f of x, you take the opposite of f of x. Then you get negative 3x squared minus 2x minus 4. As you can see, these are definitely different functions. They differ in the x squared term and in the constant term. So in this case, it matters what you do first. The negative first here or f first here. This is called non-commutativity. The order of operations matters. Like putting on your shoes and socks is not the same thing as putting on your socks and shoes. One morning I got up so early that I put on my shoes and socks in that order. I then blinked and removed my socks and my shoes and put on my socks and shoes, which is the correct order. I was kind of groggy. Okay, f of x plus 1, you plug in x plus 1 here and here. 3 times the square of x plus 1 plus twice x plus 1 plus 4. You could expand this, but this will suffice. F of twice x, well, 3 times the square of 2x plus twice 2x plus 4. Okay, here we'll expand it a bit. This 2 squares to a 4 times 3 is 12. 2 times 2 makes 4. So you get 12x squared plus 4x plus 4. Your f of x plus h is like f of x plus 1, only put an x plus h everywhere. 3 times the square of x plus h plus twice x plus h plus 4. Here we have the function x over x squared minus 16. What is its domain? Well, domain, there's no square roots of negatives. Well, this doesn't have square roots at all. And no division by 0. Well, it does divide. So we have to have x squared minus 16 not equal to 0. Which, if you solve, means that x can't be plus 4 or minus 4. X is not equal to plus or minus 4. The graph and line consists of the line with 2 points removed. Here's the question about find the difference quotient for the function f of x equals 4x plus 3. Okay, that's delta f over delta x. That's the change in f divided by the change in x. F of x plus h minus f of x, that divided by h. All right, so here we put x plus h in for here. So you get 4x plus h plus 3. That minus f of x, which is 4x plus 3, all over h. Okay, expand. You distribute the 4 over these. You distribute the negative over these. 4x plus 4h plus 3 minus 4x minus 3, all over h. A lot of terms cancel. 4x and minus 4x, 3 and minus 3. We're left with 4h over h. And then, assuming h is not 0, the h's cancel and we leave 4. If h were 0, then you get 0 divided by 0, which is an indefinite quantity, which can equal anything. And we want more specificity than that, so we say 4. Oh, here's a little more difficult one. Find the difference quotient for f of x equals 2x over x plus 3. Okay, here it's a lot more complicated. Delta f over delta x. Well, I'm going to put the one, instead of writing f of x plus h minus f of x times 1 over h. Put the 1 over h out in the front of the expression just to make it a little less bulky. So 1 over h times f of x plus h, put an x plus h here and here, twice x plus h over x plus h plus 3. Then minus f of x, that's 2x over x plus 3. All right, now we have to subtract two fractions, and so this times this minus this times this over this times this. 2x, x plus 3 here, minus 2x times x plus h plus 3 here, over x plus h plus 3 times x plus 3. Okay, the usual fraction rule. I call it the rabbit rule because it looks like a kind of a square triangular rabbit with 2 pointy ears. All right, here we go. Okay, we expand this out. So this comes 2x squared plus 6x plus 2h plus 6h. Then we distribute the minus and the 2x over all this. So you get minus 2x squared minus 2xh minus 6x. Okay, the 2x squareds cancel. The 6x's cancel. 2x's cancel. And we're left with 6h over x plus h plus 3 times x plus 3. Then the h's cancel, and we're left with 6 over x plus h plus 3 times x plus 3. And that is the difference quotient. All right, here we have a graph. Now, okay, it's evidently the graph. Later we'll see this looks a lot like a graph of a cosine function, so be it. Is it one? Is this a graph? Is this a graph of a function? Yes. Every vertical line meets it once. What's its domain? What's its range? Well, you can find the domain of a graph of a function by projecting that whole graph onto the x-axis. So it's everywhere between minus pi and pi. That's the domain. The range we find by projecting the whole graph onto the y-axis, and you get this range from -1 to 1. Its x-intercepts is where it intercepts the x-axis, here at x over 2 and here at minus x over 2. The y-intercept is where it meets the y-axis, here at 1, y-intercept at 1. Is it symmetrical? Well, is it symmetrical around? It's symmetrical around the y-axis. If you flip left for right, you get the same graph, so it's symmetrical around the y-axis. Okay, that's that for that part. Stop.